Okay, this is lecture 16, chapter 15. So on lecture 15, which we had on Monday, yesterday, 5/8, we discussed the basics of chapter 15. And as you recall, we talked a little bit about uh, translation with rectilinear motion, curvilinear motion, and then we did an example of fixed axis rotation. Now, we didn't do the third problem on the not on the homework, but on the handout. And so that one is actually completed. If you didn't, I would suggest try it on your own. The actual solution is on the lecture video that I posted for yesterday at the very end, if you want to fast forward to it. So today I want to talk about general plane motion, which is the idea of when you have a body that both translates and rotates. And so what we have is something that looks like this when we start off. So if we can, wheel's a good example, but we have other examples also that I'll show. So if you picture a wheel as shown here, you can see that as the wheel rolls to the right, you have A1 moves in a straight line, but B1 moves to a new position. And so what we can do is we can essentially break this plane motion into two parts. The translation, which is just A moving from A1 to A2, and the rotation of B1 moving to B2. Now, what that does is it allows us to take directions and vectors, and using those, we can add them together and pretty much understand where something is going to move. Now, again, all these problems are at instance in time. So we're not really going to say what's going to happen in 2 seconds from now or 3 seconds. We're going to say this is what it looks like at this point. So I'm showing this example because this is a good example of both translation, rotation. And as you can see, these both B and A are constrained so that they can move either vertical or horizontal. And so if we want to describe that, and what would be the description? It would be the velocity of B, it'd be the velocity of A, and it would be the rotation or omega of the bar AB. So it could be described as, and in this case, we pick one. So we're going to pick our A as the translating piece. And so A slides from A1 to A2. And then we're going to pick B as our rotating piece. And so B goes from B1 to B2, where we say A is our fixed point of rotation. Now, whether we do it that way or we write it the other way, where we have B being the part that moves and A being the part that rotates, it's still going to give us the same exact results in the end. And so that's what's nice about it, is we don't have to really worry about which one we pick. And you'll see as we go through some examples that there's a certain method to this. You're going to essentially, on all these problems, you're going to start with what you know and work your way through the problem to the unknowns. So this is just an example of showing how this blob has both translated and rotated. Now, another way to write this is also like here. And so here we have our blob, and we have two directions because it's both moving and translating. And what we've done is we've combined the two. And so we could see that we've said, okay, we're going to say that A is our fixed point. So if A is our fixed point, whatever the direction A is moving in, we've defined. Whatever the direction B is moving in, we've defined. But now we need to define the motion of B relative to A. And so that's where this third vector comes that we're able to add. Now, if you look to the right, you can see that all three of these vectors add as they would expected, because we know that VB is the sum of VA plus VB relative to A. And we could see that VB relative to A is always going to be perpendicular to the line between A and B. And that's an important point, because if you think about it, if something's fixed in space, then that line out here, the point B, if it's rotating about that, then the velocity is always going to be normal to the direction. So for example, if I draw this, you can see I've kind of drawn this and I want to just describe it a little bit more. So here's we have this and this, which means that this thing's rotating and it's translating. So we say, okay, well, let's say, what is the translation direction? That's A. So that's where we've defined our vector A, VA. And then we've said, well, what is our fixed point? And so we fixed our point at A. And now we're saying that, well, if it rotates in this direction, then this vector here, B relative to A, so you go from A to B, just like we talked about in class, you always go from the point of rotation to the velocity that you're looking at. And then from that, you know that that velocity is going to be perpendicular. But remember that we also know that we can write this as omega cross R. So every time we write this VB relative to A, we know that it's going to be a perpendicular vector relative to this. And so it's going to be written as omega K crossed with that vector. So in future examples, you'll see that when it's written, it'll just be literally VB is equal to VA plus omega cross R. And in this case, it's the K direction, B relative to A, just like I wrote above. So that's the important takeaway here, is remembering this. So again, why is it like that? Because we know that if you have a fixed point and you're rotating, then it doesn't matter wherever that point is, that vector is going to be tangent to it. And that's what we're saying. So now this we know could move up here, up here, up here over time, but we don't care. We're just looking at a specific moment in time. And that's the takeaway with this plane motion. So there's not really a lot of theory. It's something that I agree is a little weird at first if you haven't seen it before, which you may not have, probably haven't. And it may take a little bit of thinking before you get it. I could probably talk for the next 20 minutes, but I don't think that's going to be as much benefit as actually showing you how it works in examples and what works. So going back to what we were saying, if we take this and we look at it now again with our sliders, we see that we've drawn our sliders as that, we've fixed our point, and we've drawn our vector perpendicular, and we can see how that vector forms. Now, if we do the same thing with the next slide, notice that it looks identical. The only difference is that this vector here is pointing in the opposite direction, but otherwise the velocity, actual magnitude of speed is the same. So nothing has really changed. It's just which end you decide to fix, which end you decide to say is your direction. But regardless, these directions have been predefined, haven't they? This is constrained to there, that's constrained to there. So we know that B and A have to be pointing in the normal to one another because of this. The only difference is where is this? So it's either this or it's that. Notice that the difference is which direction the vector points to. Is it VB relative to A, or is it VA relative to B? Pretty much the same thing. All right. So I hope that makes sense. I think that, as I said, it's going to take a little bit to fully comprehend it, and there's really no shortcut. It's just practice. So let's look at an example now. And this is a pretty easy one. We start with an overhead door, and the idea is that here's our door, and it's guided by wheels at A and B, as we'd imagine. And we know that the door at this point is at 30 degrees, and we know the velocity of B, which is constrained to the to the y direction, is 2 feet per second. So what we're looking for is the omega. So how fast is the angular rotation, and how fast is D moving? So in order to do that, it's going to be a similar setup to what we saw in here, right? Because we have fixed points similar to this. So you should look familiar between this example and this example. So now that you've had a chance to look at the picture, what I would do is I would recommend is sketching it out and seeing how far you can go. So, for example, you're going to first draw the direction of A, direction of B, what you think the direction of D is, and then you're going to look at what are the vectors to get from A to B or B to A, depending on what you're doing. So let me show you, and then maybe this is too early to try one solo yet. So go ahead and stop sharing. So here's our garage door. That's how our garage door looks. So we know we have a VA looking this way. We know we have VB going down. So we're given VB as we're given it as a value. So we know that that's going to be VB equals negative 2J. All right, so we know it's going down. So what is our governing equation? Well, we know because we want to figure out what is omega for this. That's going to help us decide what D is. So we know that the garage door is going to go that way because that's going down. It makes sense. It's going to go like this. So so when you do some of these, it can be kind of tricky to see where they're going. So if you take a couple of pencils, sometimes it does help to visualize it. So VA equals VB plus VA relative to B. We know that. And we also know that we can, furthermore, always we're going to write that because we're choosing A relative to B, then we're going to then write this as VB, and then this is going to be our plus omega AB in the K, and that's going to be crossed with our A relative to B. So if you need to keep track, just remember that when you write this equation, AB, AB, and that means this vector has to be that, which also means, and again, these are all vectors, this has to go from B to A, so that there's no confusion. All right, so let's figure out what is our B to A. Well, we know that this is 5 feet long, and we know that angle is 30 degrees. So that's fairly easy to figure out. We can write, and let's just write it below, our A relative to B is going to equal negative 5 sine 30 I plus 5 cosine 30 degrees J, which I can simplify to be negative 2.5 I plus 2.5 root 3 J. All right. So I'll leave those as that. So 2.5 I, 2.5 root 3 J. So now we have that, we can go ahead and write out what our equation will look like. So VA, now VA is only going to move in the I direction. So we're going to write that as an I. And that is going to equal VB, which we know is only in the J, so that's negative 2J. And then that, of course, is going to be plus omega AB K crossed with negative 2.5 I plus 2.5 root 3 J. All right, so let me write that. Let me make that bigger. Okay, so there's that. So if we go ahead and do our cross product, we end up with VA I equals negative 2j, and then we get a negative 2.5 root 3 omega AB in the I direction minus 2.5 omega AB in the J direction. All right. Now, notice that there's no VA in the Y direction. It's 0. So what we can effectively do is we can say in the J direction, what do we have? We have 0 equals negative 2, sorry, no J, negative 2 minus 2.5 omega AB. And so because we're only looking in the J direction, we don't care about the other term or this. So now we can solve, and basically 2 over 2.5 is 0.8. We get a negative 0.8. And so our final answer, omega AB, is negative 0.8. And so because we were careful to make sure that we acknowledged the directions of everything up here, that negative down here indicates that it is indeed a clockwise omega, which is correct, is what we predicted, but the math will always show us. So that's the important part of making sure you keep track of everything up here. Had we reversed these, made that plus and that minus, then that would have changed it, possibly. Actually, it would have. So that's the omega, so we know that. So then the other part is, what is the velocity of the door? Now, if we look at the door, and let me just redraw this real quick. So here it is redrawn. Now, we know omega AB, so that's going to help us a lot because we know the direction it's going. Now, we know that the omega has to be the same throughout the whole bar. Now, D, because A is moving this way, B is moving down, D is rotating, but it's also moving. So we can't say that it's doing this, or whatever. We don't know really where it's going. So it's probably going to be something like this, but we're going to have to figure that out. That's going to be our velocity D. But fortunately, because we know B, we can do the same thing as we do with A in order to find omega. We can write the velocity of D is going to equal the velocity of B plus the velocity of D relative to B, which we know is going to be the velocity of D equaling minus 2J, and then that's going to be plus omega AB crossed with RD relative to B. All right. So just like before, only now we know omega. So now we can figure out going from B to D. We know that RD relative to B is going to be opposite because before we went from here to here, now we're going from there to there. So we switch the signs on our vector for the distance, and we get 2.5 in the I minus 2.5 root 3 in the J. All right. So the difference is we're going down this way and over. Okay. So then let's just set it up. So we know the velocity of D is going to equal minus 2J, and then that's going to be plus. Now we know it's going to be 0.8 negative crossed with 2.5 I, and then that's going to be also crossed with, or plus, negative 0.8 crossed with negative 2.5 root 3J. All right. So basically, I've just broken them down into each pieces and added them together. So if we go ahead and do our cross products, this is again K, and this is K, sorry about that. So we know that that's our omega AB, and that's our I component, and then we have our J component. So we have K cross I is going to give us a J, and then K cross J is going to give us an I. So our final answer, so we have, I rewound it, or rewrote it, sorry. So negative 2J, and then that's going to be negative 0.8K cross 2.5I plus negative 0.8K cross negative 2.5. But we know that K cross J is going to give us a negative I. So these negatives will cancel, but they'll come back because of negative I. This will be negative, and because K cross I is a positive J, it'll stay negative. So once I do my cross products, and add the J to this, I end up with velocity of D is equal to negative 3.46 I minus 4.00 J. All right. So check the work, make sure you get that. But so that makes sense because we predicted it would be down and to the left, which makes sense. It's going to be going in that direction. All right. Now, that was a fairly simple example, but I went through it slow because I wanted to make sure that we understood the vector cross products. And so, like I said in class, make sure you understand those. They're going to keep repeating themselves over and over again. If I seem to be tedious and when I'm going over them, it's not to bore you, but just to make sure you understand it. And again, some of you will pick this up really quick. Some of you might take a little longer. But I will say the first time I taught dynamics last year, this part I did have to think about a little bit. So quite a bit, actually. So it's not like it's real easy, intuitive for everyone. Okay, so let's go back. I want to do another few examples in this video. So we have that. So let's look at this one now. This is kind of the same idea. Here you have this link EB, and then you have this entire link ABD, and we can see that D is going to be able to move up and down freely. B, because it's constrained by E, is only going to be able to move left or right. And B can only move left or right because, again, if this point can't move, that point is limited to where it can go. And then A is free to go. And so A is kind of our translating point in this case. So I'll point out some things as we do this, but this is kind of consistent with the way these plane motion problems work. Is if you have a fixed link, that that does define the direction here. This is defined because it can only move in the J direction, whereas A can move in both the X and Y, and that's going to ultimately what we want to find. So I would go ahead and draw this on your paper and draw what you know, what you don't know, and then let's work through it. So here's our drawing of what we have. So we have E, B, just like this. We want to find omega AD, the velocity of B and the velocity of A. So here's what E looks like, the velocity of B. So I know that's going to have to go that way. I also know the velocity of D has to go up and down. So I have these two distances constrained. Now, if I draw my equation, VB equals velocity of D plus the velocity of B relative to D. And you probably ask, well, how do you know to do VB? Why not do like VA? Why not do VD? So the reason we do that is because we know this. We're going to start over here. We don't know this. We don't know this. So kind of like in trusses, we start with what we know and we work away. So we're going to start here. And since we know that, we're really interested in what is the velocity of B. Well, the only way to do that is to figure out this using this equation here, because the B relative to D will then allow us to find the omega. So as we know, this is going to be VB equals VD plus omega BD crossed with R B relative to D. All right. Now, if we can do this as a vector, we can do it as a scalar. Now, this problem introduces that idea. And so what I mean by that is we know D is going up, we know B is going that way. And we know that these vectors have to add to one another, don't they? So another way to think about this is if I were to draw my velocity of D going up, and I know that if my velocity of D is going up, and then I add that to my velocity of B relative to D, so this is velocity of D, then that has to add to my velocity of B. So this we know can also be written as omega BD times R in the scalar sense, can't it? So we know the distance, right? We know it's 360, and we know this velocity here. So this velocity here is equal to 1.6 meters per second. And the other thing we know is that this angle here is 30 degrees, okay, from the drawing. So make that a little bigger. 30 degrees. All right, so that's 30 degrees. So as a result, we know this is going to be a 30, 60, 90 triangle. So that's 30, that's 60, all right? And so if we set that up that way, then we can just use trig to figure out what's what. And so if we write this, it's going to look like this. So the R is going to equal 0.360 because we're in meters per second. So if we write 0.360 omega BD, that's the hypotenuse, we know that's going to equal 1.6 divided by the sine of 60 degrees, since that's the opposite side. So that allows us to solve for omega BD equal to 5.13 radians per second. All right. Now, this does require you to know which direction this is going to go, because this is a scalar, doesn't tell you anything about direction. But because this is going up like this, it's safe to, and this is going to go over, it's safe to assume that this is going to go in the counterclockwise direction, which is what we got here. So you don't need to change the sign. So we know the value, the magnitude of it. And that's the first thing. The other thing we know is that because it's BD, it's going to be the same for AD. Nothing changes. The whole thing's going to be 5 points. So we can also write omega AD is also equal to 5.13. Now, because we found this, we can also solve for VB just using tangent, right? And so we can write the velocity of B is equal to 1.6 tangent of 30 degrees, or whatever your preferred trig function is. But we get VB equal to 0.924 meters per second. All right. Now, if you didn't like this method, you could have also done it like with RB relative to D. So you could have said, okay, well, what's D? How do I get from D to B? Well, you would know that because you could go from here to here. So you know it'd be 360, negative 360 cosine 30 would be your X, and 360 sine 30 would be your Y. And then you could have done cross products here, and you would have known that VB would have only been in the I direction, and then you could have solved it in a similar fashion to how we did it the previous way. And if that's how you prefer, that's fine. Sometimes these problems are easier with triangles, sometimes they're not. The homework problem, I offered two solutions to that one, the one with the incline, and I'm going to do an example like that one, so you should be real clear on it. But in the homework solutions I offered, I I will post both ways. I'll post the way to do it with trig and the way to do it with the vectors. I think the vectors tend to be more widely accepted in terms of student use, just because I think you guys are more familiar with using them. But again, so if you don't like this, just do it like I showed before. Just go ahead, create a vector. So I can even write it R B relative to D, and that's going to equal negative 360, and you can convert this to meters, but 360 cosine 30 degrees I plus 360 sine 30 degrees J. And then you'll go ahead and plug it in here. You'll know VD, right? And you won't know VB, but you can then make it just in the J direction as before, and then you can set this equal to 0. So you have 0 equals 1.6 J, and then plus this cross product. So your only unknown will be omega, and you can do it that way also. All right, so let's continue. So we've gotten 2 of the 3 things we need. Now we want to know what is the velocity of point A. So we have VB and we have omega. So now we just need the velocity A and we'll be finished. Okay, so now we want to know what the velocity of A is. And so the thing we want to look at is that what we're effectively trying to find is, what is this velocity out here somewhere, like that. All right. But we do know that if we look at velocity of A relative to B, it's going to be perpendicular to this direction. All right. So our perpendicular is going to allow us to determine what this is. Now we know that that is just going to be equal to omega R. Well, we know omega, we know R. R here, again, was only 240 millimeters. And we know that this angle, if that's perpendicular, that this whole angle here has to be 60 degrees, right? Because if this is 30 over here, that's going to be 30 here. And then this will be 60 up here. So really what we're saying is that the velocity of AB is equal to omega R at an angle of 60 degrees. So if we do that, we get what? We get 0.240 times 5.13 radians per second. And that gives us a value of about 1.232 1.232. And that's at an angle of 60 degrees. Okay, so what we need to do is break that up and then add it. So we know that it's going to be at 60 degrees, so we know there's going to be a certain amount going this way and a certain amount going that way, right? So if we set this up, then we say velocity of A equals velocity of B plus velocity of A relative to B. So we already figured out the velocity of B. That was negative 0.924, right? Because it was going in that direction. So that's our I. And then what we're going to do here is we're going to say plus, and then I'm going to write in parentheses 1.232, and then that's going to be what? Times minus cosine 60 degrees I, and then minus sine 60 degrees J. All right. And so all I did was take this value that we found the scalar for, but we know the angle. Again, we know the angle because A relative to B has to be perpendicular to this point, right? And so we can do that. We add it together and combine, and we get it to be velocity of A ends up being about 1.873 meters per second. And then if we take the angle, it ends up being at about 34.7 degrees. Okay. So I know you can do these intermediary steps, not a problem, but that would make sense that velocity of A is going to be somewhere out here. And then this angle is going to be about 34.7. Okay. So that's another alternate way to do things. Again, get familiar with them, pick out which works for you, which doesn't. Again, it takes practice. So this one, we started with, we worked our essentially from here over to here and then over to there. Okay. All right. So hopefully this is making sense. Okay, I want to do one more example before we call this lecture, and then we'll move on in the next one. So here we have another plane motion problem. So here we're given that DE has an angular velocity of 20 radians per second clockwise. So it means it's doing this. And so we want to then determine what is the actual angular velocity of dB and what is the velocity of a point in the very middle of dB. So similar to the last couple problems we did, we're going to approach this the same way. We're going to start with dE. Now, one thing you may have noticed already is that if E is fixed, that we can quickly determine the velocity of D, because we know that if we say the velocity of D equals the velocity of E plus D relative to E, we see that if E is 0, that D and D relative to E have to be exactly the same, which is true. So the velocity of D is going to point straight up, and it's just going to be the omega times that distance, 0.15. Once we find that, we're going to set up our equation basically from this end, and then we're going to set up from that end, and then we're going to equate the two. So that's the method. So if you have an idea how to start it, I would go ahead and try it, and then let's go through the solutions. All right, so here it is drawn. You've hopefully already made your own sketch. So we have this distance 0.15, there's point E. We have the center point G that I'm referring to. And then we have the other parts, so D and B. So we can see right away that if we wanted the velocity of D, it's just omega R, 20 radians per second times 0.15 meters gives us 3 meters per second moving upwards. So then at that point, we're going to look at point D, and we're going to look at point D, we're going to look at point B. Now, because we know the velocity of D, we're going to say, well, the velocity of B is going to, of course, equal to the velocity of D plus the velocity of B relative to D, which we know now is always going to be written as omega BD plus R B relative to D. So if we write that out, then we know that D is 3 going up. So we're going to write that as 3J. And then we're going to write that as plus omega BD. And that's going to be crossed with RB relative to D. So D to B, we know it's going to be 0.6, 0.25. So we'll do 0.6I plus 0.25J. And if we do that, we end up with VB equals 3J plus 0.6 omega BD in the J direction minus 0.25 omega BD in the I direction. So we have two unknowns, so we can't do anything with this. So we're going to start and label this equation 1. Now we're going to look at the velocity of B kind of from the other end, so to speak, because we know we've determined what the omega is, right? we're gonna have the unknown of the omega, and we're gonna look at what kind of relationship can we make from this end. And so we started from this end. Now we're gonna go from this end and see what that gives. So if we look up at velocity of b, essentially what we want to do is we want to make another relationship for the velocity of b, and then we can set those two equations equal. So we also know that the velocity of b from this end, since a is fixed up here, right? We know that that is just simply going to be omega AB times or crossed with our B relative to A, right? If we write it out. So if we write that out, what do we get? We get omega AB in the K crossed with a negative 0.2 J, right? Because we're going from A to B, so we're going down 0.2 in the J. And so that essentially gives us 0.2 I, or omega AB, in the I direction. All right. So now we have a relationship for this. We have a relationship for this, right? We know that VB equals that. We know that VB equals all this. So that's my second equation. And now we can set them equal. And so this is just the normal algebra that you would do. And so if we look at, we set them equal and we separate them into i's and j's, right? Because we know all the i's have to be. So let's do that. So for the I direction, what do we have? We have negative 0.25 omega BD. And that's going to equal 0.2 omega AB. That doesn't help us much there. But if we go to J, we know that we have what? We have 3 and then plus 0.6 omega BD. But we know that this has no J, right? So that's going to equal 0. So now we can solve, right? So we get 0.3 over 0.6 gives us 5. So we end up with an omega BD equal to 5 radians per second. Actually, it's a negative 5. So radians per second. So I know omega BD is equal to 5 radians per second in the clockwise direction. If we go back and solve for, plug that in up here, we can see that that's going to cancel the negative and we're going to get an omega AB, and that's going to be a positive value of 6.25 radians per second. Okay, and so that's going to be going the other way. So again, to just a quick review, what did we do? We started here. We had this we knew, so we found our velocity d. We wrote our relationship, VB equals VD plus B relative to D, which we know is always going to be represented by this. And you ask, why can you do that? Because you know that B relative to D is always going to be the perpendicular speed. So in terms of this, it's going to be a perpendicular speed. So that's why we can put that in there. All right. We figure out our vectors, we solve, we make one equation. We do the same thing for VB. We don't know anything about VB except we do know A is not going anywhere. So we know VB is just going to be the cross product of this 0.2 in the negative J direction. And that gives us this 0.2 omega BI when we do K cross negative J. So we solve for that, pretty much we're done. So now we're not quite finished because remember we were trying to find the midpoint of G. So now we need to know what is the velocity of that midpoint. So there, just like before, we're going to say, well, we want to know what the velocity is, so we're going to have to relate it to one of these points. So what I'm going to say is let's relate it back to point D. You don't have to, but since we know what point D is, we didn't solve for point VB, did we? We could go back and do it, but since we know what D is, let's start there and make life easier. So here's what it looks like. So it's G. So D and then G relative to D, which is just BD crossed with GD. Now, fortunately, we know all of these values, so we can just plug them in, right? We know this is going to be 3J. We know that this is minus 5 in the K, so plus, and then what we'll do is we'll say minus 5K, and then that's going to be crossed with what? So the distances for the center would just essentially be half of what we had before. So half of 0.25, half of 0.6. So what do we get? We get 0.3i plus 0.125j. And that's it. And so we go ahead and figure that out. And what do we get? We get a 3j minus 1.5j plus 0.625j. And so our final answer, velocity at g, is just 0.625 in the I. Sorry, this was I. So 3j minus 1.5j, 6.25. Sorry about that. So 0.625i, and then that's half of that, so plus 1.500 in the j, all in meters per second. Okay, there you have it. So nothing really tricky. We could have found any point on here doing that method as long as we knew where it was. It's our vector, right? Because the velocity is going to vary even if the omega is the same. So hopefully that helps. Hopefully now you'll be experts. So in the next lecture, what we're going to do is we're going to do problems similar to this, except now we're going to add acceleration to it. So remember that acceleration was the only difference with that is now we have two terms, right? We just don't have velocity, but for acceleration, we have to deal with tangential and normal. And so that makes it a little more complicated, but not too much. So I would say if you understand what we did here, then you should be in good shape. So that'll be the next lecture. So thanks for listening, and talk soon.